Hello everybody, welcome back to From Rhythm to Algorithm Part 13. And today we'll be talking about complexity. Specifically, we'll be talking about the P versus NP problem. First thing we're going to do is I'm just going to read through the statement of the problem on Wikipedia, and again just respond to the things that make sense to me. I have all the gist of it up on the board. But the P versus NP problem is a major unsolved problem in computer science. It asks whether every problem whose solution can be quickly verified can also be quickly solved. The informal term quickly used above means the existence of an algorithm solving the task that runs in polynomial time, such that the time to complete the task varies as a polynomial function on the size of the input to the algorithm, as opposed to, say, exponential time. The general class of questions for which some algorithm can provide an answer in polynomial time is called class P or just P. For some questions, there is no known way to find an answer quickly, but if one is provided with information showing what the answer is, it is possible to verify the answer quickly. The class of questions for which an answer can be verified in polynomial time is called NP, which stands for non-deterministic polynomial time. An answer to the P versus NP question would determine whether problems that can be verified in polynomial time can also be solved in polynomial time. If it turned out that P does not equal NP, which is widely believed, it would mean that there are problems in NP that are harder to compute than to verify. They could not be solved in polynomial time, but the answer could be verified in polynomial time. Aside from being an important problem in computational theory, a proof either way would have profound implications for mathematics, cryptography, algorithm research, artificial intelligence, game theory is not real, multimedia processing, philosophy, not real, and economics and many other fields. This is almost a math problem. Because it's clear logically what they're trying to ask, but it's not asked correctly, and this is completely solved by the dynamic limit. The dynamic limit really, it mathematically represents every interaction in R3, which is the entire world, anything that has mass and exchanges information via radiation, which is the only way anything exchanges information, except for at the macro scale, we vibrate our vocal cords, but it's still matter moving around, and the inefficiencies of the structure, that's how we produce words. But it asks whether every problem whose solution can be quickly verified can also be solved quickly. Let's just start out with what is a proof, right? A proof establishes a fact. I say in an empirical proof says, here are the facts that establish this language. This is why we say these words. But here's the evidence. So I think the first thing to start with P versus NP is the context of the problem. Typically it was derived from the cryptography and the World War II cracking codes. And so over here you have the concept of language, linguistics, proof, logic, facts. And a huge subset underneath, you have algorithms, right? The title of this lecture series, From Rhythm to Algorithm. Rhythm is the fundamental physical principle, and algorithm is a set procedure to a given goal. A solution is the goal of a mathematical problem. But how you structure a question defines if there is a direct and definitive solution. What I'm saying that the Millennium Problems, to show that there's not even a problem anymore, what the proofs are is showing that the logic is inconsistent. It is what it is the form of all solutions for all mathematics, right? You're adding your specificity, you're adding your direction, you're adding your, what more definitive statements can I make to anything. So when you ask a question incorrectly, you just show that it doesn't reduce to this statement and the logic is incorrect. Now just some trivial derivations, right? It is what it is. Spelling a word constructs a variable. It is a word. It is A. right? And when we use the natural numbers, we classified everything that exists. So that's kind of a broader point, but right, you start reproducing all of the identity matrix. The identity matrix, in language, I is me. That is the statement of the identity matrix logically. But A is A, it is what it is. And then you say, right, happiness is content plus joy. Happiness equals content plus joy. Right? Is that true? Does happiness equal contentfulness and joyfulness? You can't prove that. Well, you might say yes, you might say no with some caveats, blah, blah, blah. A complete solution is not going to have any caveats. So I'm not going to read more of the statement of the problem because that's really the meat of what's there. But like they use Sudoku. Deriving speciality, was that hard? Is that a hard problem? Is that a complex problem? Do complex numbers exist? Do irrational numbers exist? No. Speciality is the manifestation of a personal insecurity. The natural ontology for the word complexity and complete generality is psychology. So in mathematics, there are no complex anything. But the crux of this problem is it assumes solutions exist numerically. You can say 1 + 1 = 3. You're given an equation and you solve something. You're given initial conditions. Association and analogy just pairs cliches. The language proofs just pairs logic. This is a question of mathematics, in computer AI complexity theory, but it's really a statement about language. And again, the empirical demonstration of speciality. Did it take me a long time to derive speciality? No. 2, 3, 4 years, whatever. Was any part of that complicated? No. Did a solution exist? Yes, speciality is the natural antagonism to differentiate, or the natural tendency to differentiate for sexual antagonism. So, when I was a 15-year-old kid, was it confusing to me that sexuality has influence in the world and it manifests as insecurity? No. But how long did it take me to derive those words? A long fucking time. For me personally. For mathematics as a whole, not a long time at all. So when you're saying like the polynomial time, terrible term. Gonna start my camera over. Polynomial time, terrible terminology. What is a polynomial? A polynomial is an expression of a given rank. So just to be clear of what we're talking about, time is a physical measurement of inefficiency. Polynomial is a mathematical structure. Polynomial time, just stop saying that, whatever that's trying to be. Because I've seen like polynomial linear time and polynomial quadratic time. To me, that strikes me as you're just saying whatever the highest order, the highest rank of a variable in the equation is, that's what you're saying that. Don't equate polynomial and time. A polynomial function, yes, right? F of x. X is the independent variable, that is your input, and what you get out is y. And so how does that translate directly to language in the P versus NP problem? Because the P versus NP problem becomes, so in the P versus NP write-up statement of the problem, it says, what is an algorithm? And it says, time is the number of steps it takes to solve a problem. Time is represented by a number, but time is not a number. So that is definitely an incorrect definition within the problem. Doesn't really affect the logical statement of the problem much. But like I said, the importance for the word algorithm is, right, when you're solving a Rubik's Cube or you're doing a Sudoku problem, you're guaranteed to have a solution. When you start asking about how specific is a solution in language, does the solution exist? Yes, it always does. Any logical solution is going to reduce to it is what it is. For sure, proven, done, 30,000 years ago since people started talking to whenever this planet blows up and never exists anymore. And so, just another, again, they get to try to reduce, so most mathematical problems, they'll start by saying assume this or assume that, and then it reduces a language problem to a shitty math problem. And so a lot of times for P versus NP, you'll hear talking about completeness, what is complete, what is incomplete. In graph theory, you're taking anything that's represented by a closed polygon. It includes the boundary is considered complete. Physically, we don't know what the physical bound of the universe is. So completeness at a universal level is undefined, but almost certainly, yeah. It's like I don't know. Would there be? Is there a boundary to the universe? Undefined. I don't know. I straight up don't know. But the point is any system complete? No. There are no closed systems, and the concept of mathematical completeness at the universal level today is a little outside of my reach. But for the P versus NP problem, are there sets of complete solutions in language? No. Language builds. Language develops. 50,000 dogs can't speak words. We speak words. So 100 million years there's going to be more words. So completeness is hard for me to tackle. It just as a general concept. For P versus NP, it's not relevant. Because I said your assumption is an algorithm that they can produce a solution. This word to this word is where the statement goes kind of funky. Deterministic, if it can be solved, so they'll say, if the solution exists, it's in the group P. If it can be quickly verified, it's in NP or what. I read the statement of the problem, but the logic is kind of funky. Just the P versus NP. But deterministic, is anything deterministic? Physical laws, yes. Do people have free will and choice? Yes. So, do animals have free will and choice? Yes. So just as again, in complete generality, does determinism exist? No. Right, everything's correlated, everything's related. In financial markets, the gray areas where it gets interesting, you can take two financial things and say these are directly correlated, but how about these other two things or these other three things, and they're all the same people, they're still all interacting, so certainly there's some relations, but what are they? Hard to pin down. But mathematically, bringing all of this together, when you say, does P equal NP, you're writing a mathematical equation. It is what it is. Is the more comprehensive linguistical term for the equation for the equal sign. So when you have P saying, a solution exists, that's your assumption. That's kind of funky. But do all solutions that exist can they be verified? Can you find the solution? No. Holistically, no. That is why P does not equal NP. But even more general, this is the form of the dynamic limit. Every interaction, any interaction of exchange of information is between a system with mass and it uses light to transmit that information. So you can even ask a more general statement. Forget the logic of P versus NP. Just take any statement with an equality sign. P, whatever could be represented by P, by literal definition, can't be anything else but itself from the identity matrix. It is what it is. And so deriving the dynamic limit, there's no questions. The proof by reducibility of sensorality, the thing I'm working on right now, this will demonstrate the proof of the Collatz conjecture with actual numerics. But P versus NP is a logical statement, and it's reflective of the language being an incomplete system because there are no closed physical systems, right? We're exchanging our energy content. I can go eat a cheeseburger, I'm going to weigh a little bit more than I did right before I eat it. I can go run, and I'm going to literally radiate heat off of my body and send that energy back out into the environment. So that is why P does not equal NP. In more poignant generality, this is why anytime you put an equal sign in something on the left and something on the right, and they're not the exact same symbol, not the same logical idea, whatever, they can't be the same. But more generally, does complexity exist at all in mathematical proofing? No. Speciality and insecurity manifest literally as extending and exaggerating language. So therefore in mathematics we state problems incorrectly in the wrong context. Complexity is part of psychology, the proper ontology for psychology. And thank you. That's about it I wanted to say for here. Like I said, this is close to being a mathematical problem. But when I'm talking about intelligence jumps, if you can't state a mathematical problem correctly, there is nothing. You can't produce a numeric solution. And there was never going to be a numeric solution to P versus NP or anything in logic. Now practically, you see that when you go try to train an AI system. Will you ever have an input, right? The set of inputs, how many images do you have to train an AI system on is tremendously larger than the amount of steps you need in your algorithm to get to the goal. But again, the goal in language for me right now directly for the past 2 years is say sensorality is, and then a bunch of words I already know, definitions, it would never be unclear to me. So is that complex or is that hard? No. Are there hard math proofs? No. Trying to be a less incompetent fucking animal is hard. For me it's hard. For everyone it's hard. Self-filtering your language. Physics, the words you speak. Physics and you is the filtering process. Yeah, that's all I wanted to say for P versus NP, and they clearly do not equal one another. So, thanks for watching.